Hello everyone, I am Alba Jiménez Pagán, and today I'm going to explain you the main findings of my PhD thesis entitled Development of Laser-Based Diffusion Processes in Germanium for the Manufacture of Low-Cost Thermophotovoltaics. So I will start this presentation by giving you a brief introduction to TPV technology, followed by the main objectives that have been addressed during this PhD. Then I will move to the experimental part, first talking about surface cleaning and passivation of germanium, followed by the phosphorus doping by means of laser diffusion processes, and localized omic contact formation by means of the laser far contact method. By integrating all of the different experimental steps studied and developed, I will also show you a first prototype for an integrated bad contact cell, and I will end up this presentation with some main conclusions and next steps. So let's focus first on the introduction. So TPV systems convert thermal radiation into electricity from various heat sources, such as industrial waste heat, combustion of fuels, concentrated solar or nuclear energy. The system is composed of a heat source, a thermal emitter, and a TPV cell. So heat is applied to the thermal emitter, which becomes incandescent, and transfers the heat by radiation to the TPV cell, which directly produces electricity by the photovoltaic effect, with some heat losses. So in the case of having a back surface reflector at the backside of the TPV cell, photons with energy lower than the bandgap can be reabsorbed by the emitter, not contributing to efficiency losses. In fact, if you take a look to the definition of efficiency for TPV system, you can see that there are two main ways of increasing the efficiency of the system, by increasing the electrical output power, but also by increasing the reflective power. TPV technology is a promising tool with a wide range of different applications, such as novel thermal energy storage systems. It can be also applied for waste heat recovery, to increase energy efficiency in industry, or for distributed combined heat and power. In the past, it has been also used as a power source for hybrid vehicles, and another appealing application is of grid generators, which are suitable for isolated regions or space applications. If we take a look to the TPV efficiencies reported in the literature, you can see that efficiencies in the range of 30% have been already demonstrated. Nonetheless, most of the most efficient semiconductors are 3-5 materials, which represents a constraint for TPV technology, which suffer from its high cost per output power for a major commercialization of this technology. And this is so because the 3-5 substrate represents the largest single cost of TPV modules due to its high cost per unit of area. In this regard, germanium has been historically considered as a low-cost alternative with a substrate price several times lower than some 3-5 semiconductors. However, one of the constraints of germanium is its low efficiency, and as you can see here in the graph of the right, where the thermodynamic efficiency, which is the experimental current record efficiency versus the ideal limit, and this is represented for different materials, you can see that in the case of germanium, its current efficiency of 16.5% represents just the 27% of its upper thermodynamic limits, which means that there is a lot of room for improvement. And in fact, this record efficiency has been achieved by using high capital cost techniques, such as metal organic vapor phase epitaxy, which means that there is a need for low cost and high efficiency germanium TPV cells. That's why in this PhD thesis we have reconsidered the use of germanium for TPV, and in order to increase its efficiency, we have proposed the use of an intermediated backpoint contact TPV cell architecture. This cell architecture, which has both contacts at the backside, is the cell architecture which has the record efficiency for silicon PV, and it has several advantages, especially for its use in thermophotovoltaic applications. One of them is the elimination of the shadowing factor, which means that there is no trade-off between absorption of light and series resistance losses determined by the area covered by the front electrodes. It can also allow the development of highly packaged TPV modules, since it allows linear planar interconnection, enabling a TPV cell assembly very tightly. And another advantage for TPV is that since most of the back surface is covered by a dielectric and a metal, and the doping is just punctual, the back surface acts as a mirror, reflecting back to the thermal emitter the photons which has not been efficiently absorbed. Nonetheless, this cell architecture has some main challenges to face. For instance, excellent surface passivation needs to be achieved, since most of the carrier are generated in the front and need to be collected at the backside, and also it's not straightforward to achieve localized punctual emitter formation and local ohmic contact formation in a cost-effective way. So before moving to the experimental part, let me show you very briefly a timeline of the main activities and progress developed during this PhD. So I started the PhD in October 2017. I was doing a preliminary work in which I was making doping of germanium by means of furnace diffusions, and then we start making some collaboration with central laser UPM, starting some trial about doping by means of laser diffusion processes. However, this work was too preliminary, so it was not included in this PhD presentation. Then we start a collaboration with UPC, where we were doing some surface passivation experiments, since they are expert on passivation of silicon for photovoltaic applications. After achieving good surface passivation, we moved to the development of phosphorus doping by means of laser diffusion processes, first in large area, and this was done in collaboration with University dell'Istituto di Padova. Then I start transferring the knowledge about the impact of the laser parameters into localized emitter formation and localized ohmic contact formation, again in collaboration with central laser UPM. After a while, in April 2021, we were able to install a laser system in our lab, and I was the person in charge for the commissioning. And when we install the laser system, we have repeat again these experiments, and since we obtain better results, these are the results that are included mainly in this presentation, apart from large area emitters. After we have developed all of the previous steps, we have fabricated a first prototype of an IBC cell, which I will show you later. And these are the main public and private funding that I have achieved during this PhD. And the result of this work has resulted in several contributions to conferences and in the publication of several articles in peer-reviewed journals of high impact factor. So let's move to surface cleaning and passivation. So in order to achieve good device performance when using germanium, it's of utmost importance to achieve a free cleaning surface which has no organic contamination and germanium oxide. This is especially important in the case of germanium, since germanium oxide is thermodynamically unstable and it forms a very poor interface with germanium, which has a high density of surface state. In this regard, hydrogen plasma cleaning has been agreed in the literature as one of the most efficient cleaning methods for germanium surface. And since it can react with carbon, and it also volatilizes germanium oxide at the same time. In our case, we have performed the hydrogen plasma cleaning in situ in the PCVT reactor, where we deposit also the stack used for passivations. So once we have achieved a clean surface, we proceed with the deposition of the amorphous silicon carbide stack, which we use for passivation purpose. And in order to evaluate the degree of surface passivation achieved, we have made use of contactless photoconducting decay measurements. We have optimized the process by changing the hydrogen plasma cleaning duration and also the process temperature. It is important to note that the process temperature affects not only the temperature of deposition for the amorphous silicon carbide layers, but also the temperature at which the hydrogen plasma cleaning is performed. So as you see here in this graph, where the effective carrier lifetime is represented as a function of the plasma cleaning time, you can see that for the lowest temperature deposition, T1, an improvement in the effective lifetime can be achieved by increasing the plasma cleaning duration. But anyway, we are achieving effective carrier lifetime always lower than 50 microseconds. In the case of increasing the temperature, the impact of the hydrogen plasma cleaning duration is enhanced, and the most drastical enhancement in terms of increasement of effective carrier lifetime is achieved for the highest temperature deposition, T3, in which effective lifetime higher than 600 microseconds were achieved, which correspond with an upper limit for the surface recombination velocity of less than 15 centimeters per second. And this is just a picture of me and my co-director at UPC facilities where I performed all of these experiments. But how would our result within the state of the art? So as you can see here, there is a very strong correlation between the effective carrier lifetime and the doping level in germanium. And in our case, the more than 600 microseconds of effective lifetime were achieved for a doping level of 310 to 15 cubic centimeter. Apart from using this kind of wafers, we have tested also our passivation in intrinsic wafer, achieving more than 1 millisecond of effective lifetime. And this means that our results are in the range of the best one reported in the literature for the same level of doping. So now that we have tested and tried and checked that the good quality of the surface passivation achieved, we want to also test the thermal stability of the passivation stack. And to that end, we have conducted a rapid thermal annealing to passivated germanium wafers. And in this graph, you can see the effective carrier lifetime as a function of the annealing temperature in forming gas for 60 seconds. In this graph, you can see the two different processes temperature for the deposition of the amorphous silicon carbide stack. The black line, which represents the lowest temperature deposition, T1, and the blue lines that represents the highest temperature deposition, T3. As you can see, regardless of the deposition temperature, all of the samples show an initial improvement in the effective carrier lifetime with temperature. However, after a certain temperature, both of the deposition conditions suffer from a deterioration of the effective lifetime. And what is different, depending on the deposition temperature, is the onset of degradation. So in the case of the lowest temperature deposition, T1, the onset of degradation starts at 400 or 450 degrees, whereas in the case of the highest temperature deposition, the deterioration starts slightly later at 500 degrees. And this highest thermal stability for the highest temperature deposition could be explained by the enhancement in the blister formation for the lowest temperature deposition as the annealing temperature was increased. Since the samples passivated with amorphous silicon carbide deposited at the highest temperature deposition were the ones that generally achieve higher effective lifetime and also have a higher thermal stability, this is the process temperature that we have used for the rest of the experiments. So let's move now to phosphorus doping by means of laser diffusion processes. So the laser doping process, also called pulse laser melting, is a low-cost technique which can be used in order to fabricate advanced cell architecture in a cost-effective way. But first, before explain you why this is a low-cost technique, let me explain you a bit the physics of the laser-based diffusion process. So in case of having a substrate, in this case germanium, covered by an overlying dopant source, together or alone with a dielectric layers, let's assume here that in the presence of a dielectric layer, after laser irradiation of this sample and when using energy about energy fluences above a certain threshold, what happens is that melting of the semiconductor takes place and also the dopant source and the dielectric phase change. So we can achieve simultaneous opening of the dielectric layers and diffusion of dopants in liquid state at a rate of several orders of magnitude higher than in solid state. And after we have stopped laser irradiation and the energy has been dissipated to the surrounding, we achieve also a very fast epitaxial recrystallization of the semiconductor in the order of meters per second. So why this is a low-cost technique? It's because it allows to reduce a lot the fabrication complexity by simultaneous opening of the dielectric and doping underneath, which means that there is a need for less photolithography steps. It also reduces the thermal budget as compared with diffusion of dopants in furnace and also in MOVP reactors. And of course, if we are able to reduce the energy consumption for the fabrication process, we also reduce the fabrication processing cost. And although it is not exactly related with low cost, but it is also an important feature of the laser doping process, this process helps to increase the level of doping because above the solid solubility of a certain impurity, and this is because of the very fast epitaxial recrystallization, which efficiently trap the impurities during recrystallizations. So in the experiments performed about laser diffusion, we have mainly used two different laser systems. The first one is an steamer laser with a top hat energy distribution, which means that the light intensity is almost constant regardless of the position, leading to the formation of homogeneous full area emitters in the order of 5 per 5 square millimeters. And we have used also a Gaussian, neodymium neutron orthogonalite laser with a Gaussian energy beam profile, which means that the light intensity is much higher in the center as compared with the surroundings. And this is the laser system that we have used for localized punctual emitter formation by creating a matrix of different number of spots. And this is how it looks a spot made with this laser, which has about 6 micron of diameters. So let's focus first on steamer laser irradiation in big area. This is the laser system that I have mainly used, which is an steamer laser, which is whose gain medium is a mixture of an halogen and a noble gas, in this case krypton fluoride, which emits in the ultraviolet range, specifically at 248 nanometers with a pulse width of 25 nanoseconds. So I have analyzed 3 different dopant strategies with this system. In the most simple case, germanium is covered by a spin-on dopant layer which contains phosphorus, and after curing this film at 200 degrees, we can proceed with the irradiation by a laser beam, creating homogeneous large area emitters, such as the one shown here in this picture. So in order to analyze phosphorus introduction into germanium, we have used secondary ion mass spectrometry measurements. And first, we have analyzed the impact of changing the energy fluence for a fixed number of pulses, being the energy fluence, the delivered energy normalized by the laser beam area. So as you can see here, where the phosphorus concentration is represented as a function of depth, increasing the energy fluence always result in an increased junction depth, which is a result of the higher melting time and therefore higher melting depth, because of the higher energy density used. Increasing the energy fluence also affects the phosphorus concentration, which first increased due most probably to an increased availability of phosphorus due to a higher heating of the spin-on-dopant layer, and also because of the higher overall melting time, because of the higher energy density. And then the phosphorus concentration starts to decrease, most probably due to exhaust of the dopant source and also phosphorus out-diffusion, which means that not all the phosphorus is introduced to germanium, but it is also partially evaporated. If we analyze here the impact of the number of pulses for a fixed energy fluence, you can see that increasing the number of pulses always increases also the junction depth, and this is a result of the diffusion and redistribution of dopants already incorporated during the first pulses. And in terms of the phosphorus concentration for this energy fluence, we have observed a reduced concentration of the phosphorus at the surface, and this is because of the diffusion to deeper regions of phosphorus into germanium, and also to phosphorus out diffusion as in the previous case. Phosphorus out diffusion, for instance, is very clear in the 32 pulses condition because of this positive slope in the phosphorus concentration near the surface in the secondary ion mass spectrometry measurements. In order to analyze how much of this phosphorus is electrically active, we have performed van der Pol measurements, and in this graph I show you the whole mobility as a function of electron concentration. The dashed line it is the relationship between these two parameters, which was experimentally demonstrated by Whisker Plots in the 60s for strongly doped N-type germanium. And these are the different relationships for different laser conditions that we have obtained in our work. So as you can see, we have achieved active concentration higher than 10 to 19 cubic centimeter, and more importantly, you can see that the electron concentration follows the expected trend for the whole mobility. And this means that the laser irradiation is not likely to introduce any detrimental effect, which enables scattering of carriers apart from ionized impurities. So now, if we move to the second dopant strategy, we have mainly used the same dopant source, the spin-on-dopant layer, but this time we have first deposited the amorphous silicon carbide used for passivation, and then we have deposit the spin-on-dopant layer on top. And this is done in order to achieve simultaneous opening of the dielectric and doping underneath. So once that we perform laser irradiation in this kind of samples, one thing that is very important is that not only phosphorus but also carbon and silicon coming from the amorphous silicon carbide stack are incorporated into germanium, creating an alloy of silicon, germanium and carbon, which is phosphorus dope. So if we analyze first phosphorus introduction as a function of the number of pulses, we can observe a similar tendency down for the first doping strategy. As you can see, increasing the number of pulses increased junction depth and also reduced the phosphorus surface concentration. In terms of silicons, similar trends as for phosphorus has been detected, with increased junction depth and reduced surface concentration as the number of pulses are increased. And also, it's important to note that very similar diffusion lengths are obtained for silicon and phosphorus, with a relatively narrow introduction into germanium for the one pulse condition, and with a wider diffusion length as the number of pulses increases. In terms of germanium, you can see that for the one pulse conditions, the germanium concentration is lower than in the rest of the casings, and this is because the near surface is plenty of silicon and carbon. But as the number of pulses increases, the germanium surface concentration increases, which means that germanium is diffusing toward the surface. In terms of carbon, we have seen a very different diffusion behavior, with a relatively narrow diffusion length, where the impact of the number of pulses is rather low. And this high concentration at the surface and this short diffusion length could be explained by the low solid solubility of carbon in germanium, which can make it to precipitate and segregate to the surface. So in this case, we have also analyzed the Hall mobility as a function of the electron concentration. And as you can see here, most of the conditions does not follow the expected trend for the electron concentration and the Hall mobility. Even though we expect a slightly lower Hall mobility because of the silicon and carbon introduction into germanium as compared with pure germanium, you can see that the 16 pulses condition is very close to the experimental relationship demonstrated by Fistol, but in the case of 1 and 8 pulses is very far away from its theoretical expected value. And this means that for these two laser conditions, most probably laser-induced effects have been created, and that's why there is a higher scattering of carriers. So in order to analyze laser-induced effect, we have analyzed the crystallinity of the samples by using high-resolution X-ray diffraction and in the triple axis configurations. And as you can see, for a large number of pulses, 8 or 16, we have detected a new crystalline phase whose out-of-plane parameter is smaller than germanium, which means that it is compatible with the formation of a silicon-germanium alloy. In contrast, for the 1 pulse conditions, we have not detected any new crystalline phase, and only the germanium substrate is observed, but with a slightly higher full width half maximum, which could be indicative of some third-time-induced damage, but this needs to be corroborated. That's why we have also performed Rutherford backscattering measurements in channeling mode. Here you can see the total number of detected ions normalized to the total ion beam charge as a function of the energy and the number of pulses. I would like to draw your attention to the highest energy, which corresponds with the near surface of the samples. And as you can see here, there is a very big peak, which indicates surface damage for low number of pulses from 1 to 4. And this peak vanishes as the number of pulses is increased up to 8 and 16. Moreover, this is observed at the same time that there is an overall reduction of the yield, which is correlated with an enhanced crystallinity, and this happens at the same time also that the silicon peak disappears. This silicon peak could have disappeared because of a lower concentration of silicon, and also because at the beginning it's possible that silicon is introduced at interstitial site and later in substitutional sites, and that's why it cannot be detected by this technique. This means that at low number of pulses, most probably the ineffective epitaxial recrystallization is hindered by the high amount of silicon or by its introduction in interstitial sites. In order to analyze and further understand the qualitative enhancement in terms of crystallinity as the number of pulses is increased, observed by the X-ray diffraction measurements and Rutherford backscattering measurements, we have also performed transmission electron microscopy measurements. And as you can see here, for the 1 pulse condition, there is a polycrystalline near surface, which is also corroborated by the diffraction pattern, which shows different crystal orientations. Contrary, for the 8 pulses conditions, the near surface is already monocrystalline, but still with some defects. Unfortunately, the 16 pulse laser condition, which was the best ones in terms of crystallinity according to X-ray diffraction measurement and Rutherford backscattering measurements, could not have been analyzed by TAM. And now we move to the third dopant strategy, which we call pass-up technology. In this case, we have changed the dopant source, and the dopant source is an N-type dope amorphous silicon carbide layer introduced as an intermediate layer in the passivation stack. And after laser irradiation, in this case, we obtain similar results to the second dopant strategy, with simultaneous opening of the dielectric and doping underneath, but with the introduction of large amount of silicon and carbons. So, if we analyze the crystallinity as a function of the number of pulses, you can see that again, at low number of pulses, in this case 4 or 8, there is a very large damage peak, which corresponds with surface damage, and after increasing the number of pulses, we observe an overall reduction of the crystallinity, which is an overall reduction of the yield, which is related with the crystallinity enhancement explained before. So, similar tendencies as compared with the spin-on dopant passivity in germanium has been observed. So, if we analyze now the electrical activation for this doping strategy, you can see here where the active dose is represented as a function of the number of pulses and the energy fluence, that the major influence of the energy fluence is at the lowest number of pulses, and it has a rather low impact as the number of pulses is increased, which means that in order to enhance the electrical activation, we need to use a high number of pulses. And if we compare with the result of the spin-on dopant and passivity germanium, which are represented here, you can see that again the most influential parameter is the number of pulses, since there is a threshold above 4 pulses to drastically enhance activation with a lower impact of the energy fluence conditions. And very importantly, you should note also that regardless of the laser conditions, in all cases, the passed-up technology has led to increased electrical activation as compared with the spin-on dopant and passivity germanium. Now that we have analyzed the phosphorus introduction into germanium and also the electrical activation, achieving a good crystallinity when the laser conditions are optimized, we have fabricated some diodes in order to validate our technology. So in the case of the spin-on dopant on passivity germanium, we have used palladium, titanium, palladium, silver as an ohmic contact for N-type germanium and aluminum for ohmic contact formation to P-type germanium. As you can see here, where the dark IV characteristics are represented for this technology, you can see that rectifying behavior has been achieved, but there is a very high leakage current and also shunting and very high recombination in forward bias. And if we compare with diodes fabricated with passed-up technology, we can observe that we have already improved this technology, achieving a lower leakage current and also lower shunting and recombination in forward bias, which means that passed-up technology has lead to better diode behavior and also electrically active phosphorus dose, which means that this is the best technology to dope germanium and is the one that we have used for the rest of the experiments. So now let's focus on punctual emitter formation by the neodymium yttrium orthogonal laser system, which is the one shown in this picture. As you can see here, this laser system, which is a diode pumped solid-state laser, this laser also emits in the ultraviolet range, this time at 355 nanometers, with a pulse width of 22 nanoseconds. So in order to analyze the most suitable conditions, laser conditions, for localized punctual emitter formation, we have proceeded directly to diode fabrication. And to that end, we have made the laser irradiation process in areas of 9 square millimeter, which contains 15 per 15 spots with a separation between them of about 200 microns. And this has been done in metallized square areas of 9 square millimeters. For ohmic contact formation, we have used aluminum without any other additional temperature steps. And for ohmic contact formation into N-type germanium, we have mainly used 2 different metal schemes, which are palladium, titanium, palladium, silver, and aluminum. Palladium, titanium, palladium, silver is the one that is commonly used in the literature, and aluminum we have tested also because it could imply a simplification of the fabrication process, and it could be used also for PT germanium. So let's focus first on palladium, titanium, palladium, silvers. Here in this graph you can see the dark IV characteristic of diode fabricated with different number of pulses, and as you can see, as the number of pulses increases, the leakage current is reduced, and also the recombination and shunting in forward bias with low contribution to series resistance losses. If we analyze now the impact of the number of pulses for aluminum metallized diode, you can see the same trend for the number of pulses. However, the leakage current and the shunting is generally high for the aluminum metallized diode, and especially the series resistance losses. If we analyze also the impact of changing the laser power, you can see that a very high increase in the leakage current and in the level of shunting was detected for laser power conditions higher. So here in this picture I just wanted to show you the impact of the laser condition of the morphology on the morphology of the laser spot when increasing the laser power, and also with increasing the number of pulses. As you can see, when increasing the laser power, there is an increase in the diameter size and also in the amount of molten splashes surrounding the laser spot, which can deteriorate surface passivation. In terms of the number of pulses, we know that it will increase the junction depth, but this cannot be detected in this kind of picture with just an optical microscope. And well, the best laser condition for diode fabrications were for both metal, the lowest laser power and the highest number of pulses. Also, apart from testing two different metals, we have analyzed the impact of a different amorphous silicon carbide thickness. First, we have used 45 nanometer thickness, and then we have increased it up to 180. And we have used palladium, titanium, palladium, silver for the fabrication. So if we analyze here the impact in terms of the dark IV characteristic, you can see that there is an increased leakage current and a higher recombination and series resistance losses for the highest thickness, and this could be explained by a higher incorporation of silicon and carbon into germanium during laser irradiation. In order to understand the most limiting mechanism in our diode, we have used the 1 and 2 diode model for the fitting, which is represented here. So I don't want to go very much into detail, but as most of you probably know, the IV characteristic of a solar cell can be characterized by this equivalent circuit and these equivalent equations. And the first part represent the recombination at high voltage in the quasi-neutral regions, whereas the second term of the equations represents the low voltage range, which accomplishes for recombination in the space charge region. And well, the main parameters that have been used for the fittings are the saturation current densities, J01 and J02, which depend on the material quality, the ideality factor N1 and N2, which accounts for how much is the diode far from ideality, and also the series resistance and the shunt resistance losses. So since in the literature some people let the ideality factor as a free parameter, and in other cases is used as a fit parameter, we have performed different kind of procedure for the fitting in order to analyze how much the rest of the parameter can vary in case we use it as a free or as a fixed parameter. So in the first case, we have analyzed, we have made use of the two diode model in the first case using N1 as 1 and N2 as 2 according to the literature. In the second case we have fixed N1 as 1, but we have let N2 as a free parameter in order to account for deviation from ideality. And in the third strategy we have use of the one diode models, which means that the second part of the equation vanish, and in this case we have used N1 as a free parameter. So in order to account for a spread and center of our data set depending on the three fitting procedure, we have used box and whisker plots like the one I show you here, in which the straight line represents the median and the whisker represents the upper and lower limits for the fit parameter depending on the fitting procedure. So as you see here, for the shunt resistance, which is a parameter which accounts for alternative paths for the carrier instead of being injected in the PIN junction, we have observed that increasing the number of pulses improve the shunt resistance, increasing it, and also the best laser power conditions are the black line, which are the lowest laser power conditions. So even if we are able to optimize the shunt resistance by optimizing the laser conditions, maximum shunt resistance in the order of 100 ohm per square centimeter were achieved, which means that the improvement by changing the laser condition is rather moderate. And this is very far away from ideality in which shunt resistance should be infinite. In terms of the saturation current density, G02, which represent recombination in the space-charged regions, we have observed a higher variability depending on the fitting procedures as compared with the shunt resistance, but still a trend with the laser parameter is observed, in which a reduced J02 can be achieved by lowering the laser power or by increasing the number of pulses, which means that the same laser conditions should be used to improve shunt resistance and J02. However, minimum values of J02 are in the range of 10 to minus 4 amperes per square centimeter, which are still rather high. So now that we have analyzed diode behavior by the different fitting procedure, we have end up with the conclusion that our biggest concern is in terms of shunting, and these shuntings could be created by crack formation in the laser doped region due to thermal stress because of laser irradiation, and it could be also a consequence of undiffused regions between the dielectric and the laser doped regions, which happen when the opening of the dielectric layer is wider than the extension of the laser doped region. And this is especially likely to happen in the case of using Gaussian profile, such as the one we are actually using. Nonetheless, there are some potential solutions to improve these shunting and recombination problems. For instance, the use of a beam shaper, which allows to transfer the Gaussian beam profile to a top hat energy distribution, which means that a more homogeneous doping could be achieved. And this beam shaper also increased the diameter size, which means that it reduced the energy fluence that received the sample for the same laser power. Also, the use of this beam shaper could be good because since the energy profile should be cut, it will reduce a bit more the laser power of the system, and we are already in the using the lowest laser conditions that the system enabled. Also, we can apply chemical or thermal treatment after the laser irradiation, which could reduce the number of laser-induced effects. And we can also make use of advanced metallization techniques, such as photoplating, which is selective and only deposit the metal in very heavily doped regions, which means that cracks or undiffused region in these regions the metal will not be deposited, reducing the likelihood for shunting. Also, we could use a more conservative doping process in which first laser doping is performed and the passivation the passivation layer is deposited later with a subsequently step for opening of the dielectric layer. So let's move now to the last step for the intermediate contact cell fabrication, which is the localized ohmic contact formation by means of the laser fired contact. In this technique, laser firing of a metallic layer provides opening of the dielectric layer simultaneously without diffusion, in creating all-doped regions in a localized pattern. Note that the n-type dope amorphosilicon carbide layer, which is used as a doping source, has been kept in order to analyze if overcompensation of n-type dopants can be achieved by aluminum diffusion during the laser-fired contact method. In this regard, two different aluminum thickness has been tested, 1 and 2 microns, and the process consists on, as I said, on the irradiation with a laser source, and to that end we have used square metallized areas of 4 square millimeter, and to evaluate the quality of the contact at the semiconductor metal interface, matrix with different number of spots has been used. And this is just a picture of the laser fired contact spot created by the new Dimitri orthogonal laser system. So in order to analyze the electrical quality of the metal semiconductor interface, usually the transfer length method is used, being the specific contact resistance the figure of merit. However, since for transfer length method we need large areas homogeneously doped, and this is not our case as we are analyzing localized back surface field for ohmic contact formation. We have made use of the method proposed by Ortega et al., in which the electrical laser fired contact resistance measure is it not only includes the specific contact resistance but also a spreading resistance term, which accounts for the current distribution to the bulk. So as you can see here, where the laser fired contact resistance is represented as a function of the number of pulses for different laser power conditions, you can see that the laser fired contact resistance is rather high, as in the case of the lowest laser power conditions, but it improves as the laser power is increased, and this happens until a certain laser power, above which the laser fired contact resistance start increasing again. If you see here the tendencies with the number of pulses, similar trends are obtained for most of the laser conditions, in which a worsening of the laser fired contact resistance is observed when we increase the number of pulses from 2 to 10 pulses, with a slight improvement when we increase it from 10 to 100 pulses. So the best laser conditions in general are the intermediate laser power condition tested and the lowest number of pulses. If we analyze here the spreading limit, which is determined by the resistivity of the wafer and the laser diameter size, we have seen here that for the base laser conditions we are very close to the physical limits, which means is an indicative of the high quality of the electrical contact achieved. And if we want to analyze the specific contact resistance, which is the figure of merit usually used, we can calculate it by using the laser fired contact resistance minus the spreading resistance. And doing this calculation, we have achieved a minimum in terms of a specific contact resistance in the order of 210 to -4 ohms per square centimeter. So let me show you finally the first prototype for an intermediate bad contact. So first I will show you the proposed manufacturing process, which starts with surface cleaning and passivation in the PCVD reactor including the N-type dopant morphosilicon carbide layer used for dopant purpose. So in order to introduce N-type dopant, we perform laser irradiation at a certain areas, achieving punctual emitter formation. Afterwards, we proceed with deposition of metals and photolithography steps to define the different regions at the backside, followed by the laser fire contact method to introduce aluminum and for ohmic contact formation to p-type germanium. Note that in this case, for ohmic contact formation to N-type germanium, we have used also aluminum just to simplify the process in this first prototype. And this is just a picture of the final structure of this cell. And well, if we analyze the dark IV curve of the IBC first prototype and as compared with the double side homogeneous diode achieved by steamer laser irradiation, you can see that already we have achieved a considerable reduction of the leakage current and the recombination and shunting in the case of the IBC cell, and this is most probably related with a lower laser irradiated area. If we compare now with the diodes fabricated with punctual local emitter formation with the two different metals, palladium, titanium, palladium, silver or aluminum, you can see here that more or less similar leakage current and recombination are observed in forward bias and reverse. In the case of forward bias, up to 150 millivolts, but after that, the IBC have or the aluminum diodes have more serious resistance losses as compared with palladium, titanium, palladium, silver, which means that in the next steps, most probably we will need to use different metals for the ohmic contact formation to N or p-type germanium. So let me finish with some main conclusions and next steps. So the main step for cost-effective fabrication of germanium IBC TPV cells have been studied and developed, and in terms of surface passivation, we have achieved effective lifetime in the range of the best one reported in the literature, and this has been achieved by optimizing the in-situ plasma cleaning, pre-treatment, and the deposition temperature and deposition annealing conditions. Full homogeneous formation by steamer laser irradiation has been performed using spin-on dopant and pass dopant as dopant sources, and we have achieved the highest active dose regardless of the laser condition for pass-dop technology. Laser-induced effects were effectively prevented on Berghofer, but they were detected on passivity germanium either by spin-on dopant or pass-dop technologies. Nonetheless, enhanced dopant activation and crystallinity could be obtained in passivity germanium by increasing the number of pulses, and contrary, in the case of Berghofer, increasing the number of pulses causes out diffusion. In terms of localized punctual emitter formation, the best laser condition were the minimum laser power and the largest number of pulses, and the lowest level of recombination, shunting and series resistance losses between the different set of experiments performed were for the thinnest amorphous silicon carbide layer and the metallization with palladium, titanium, palladium, silver, being the main concern in all of our diodes, shunting and recombination. In terms of ohmic contact formation by the laser fire contact method, we have achieved minimum specific contact resistance in the order of 2⁻⁴ ohms per square centimeter, being the best laser condition, the high power condition, and low number of pulses, contrary to the best condition for emitter formation. Nonetheless, these are the best laser conditions to reduce the specific contact resistance, but the laser-induced effect should be still analyzed, since there should be a trade-off between induced damage and minimizing the contact resistance. So as a future work, as our main concern is shunting and recombination, we will need to do more work about characterization and mitigation of laser-induced effect, for instance, using some of the potential solutions I've told to you earlier. And in case we resolve the formation of laser-induced effect, we could implement all of the developed technology in an IBC germanium TPV cell which could be characterized in real TPV conditions in our lab. And this cell architecture, the IBC, it is especially suitable for the development of advanced TPV cells, such as, for instance, the terminal thermoionic PV device, and also for thermoionic enhanced near-field TPV device. And these are the publications that I have in peer-reviewed journals, the interventions in international conferences, and the project I have been the principal investigator. And these are the main institutions and projects that I would like to thank. So thank you all for your attention.